which is better than, lower than 10 to the minus 4 torr, right? 10 to the minus 4 torr. And usually as a rule of thumb, this you can get 10 to the minus 4 torr. People who work in chemistry lab know that you have a mechanical pump, right? Little mechanical pump, oil-based pump, often quite noisy, and those pumps can get you close to 10 to the minus 4. Usually those pumps get you 10 to the minus 3 torr and so forth. Okay, so this is called high vacuum, right? This is called high vacuum. 10 to the minus 3 to 10 to the minus 6 torr are known as high vacuum. But we want to see why we need even better than this. Why we need ultra high, not just high vacuum, to do this. And all because we want to lengthen this mean free path, and so that it doesn't collide before it hit another atom, when the charged particle have a chance to interact with the surface of interest. Okay, so let's take a look at this. And one of the reasons is that how long, when you make a measurement, how long can you keep, how much time you need to make the measurement. So duration of experiment versus before your surface get contaminated. Because if you have in not a good vacuum, of course there are other charge, other particle in the air or something like this. Air, of course, can then interact with your material, and then you would either build a carbonized surface, or oxide surface because of that. And you definitely don't want to study those because you are not interested in the oxide or carbide surface of your material. You are interested on the material itself. So you need a way to clean them and then keep it clean, right? Keep it clean before you finish the measurement. So you should have a way to keep it clean enough so that you can complete the measurement. So here's a very quick way that I want to tell you about on how to estimate the amount of time that you need to. I'm just getting online, so in case I need the so this is a rough estimate. It's a very estimate of the kind of time that you can see. So here I define a couple of simple things. I define something called N. You can think of N as the surface density or the flux, right? So N is defined as the average number of particles hitting 1 centimeter square surface, right? 1 centimeter square. So you can think of it, if you think of a volume of 1 cubic centimeter, 1 cc, so the picture I have is that you have a charged particle beam coming down onto your surface, and you really want to see what happened to the interaction per area. So I like to define a flux sort of heating this. And so if you use simple kinetic gas field, which I don't want to go into, you can show this flux or surface area if you like, interaction area, is proportional to, of course you can sort of imagine it should proportional to the number density, right? The number density, how much gas you have already in this volume. So C here is the gas molecule or gas particle, if you like. It doesn't have to be molecule. It could be cluster or it could be atom as well. So it doesn't need to be molecule. It's just gas particle per cc. So it's just volume density, if you like, the density of this material, of this gas that you have, that you want to pass the electron beam through. And then V here is the mean thermal velocity. So you're talking about moving this charged particle or a beam particle through this volume of gas in this density. Okay, so you're sending this beam through, and you got the flux. So this is number density times the thermal velocity to give you the flux essentially. And you can further show that this flux is related to essentially using ideal gas law. I think there's a question in the first assignment. I will put the first assignment online soon. To work out using ideal gas law, we all know ideal gas law, to derive this equation. So I won't go into it. There's some hint on the assignment, so people can do this without too much problem. So the flux or the surface density, if you like, is proportional to, right, is 3 times 10 to the 23rd, roughly proportional to the pressure, square root of the molecular weight, and the square root of the temperature, and in the appropriate unit. So this is centimeters per centimeter square and per time. So that's the unit. So this is called like the amount of gas at a particular pressure and temperature that you can work out. Okay. So this is roughly the flux density relation to pressure and time, and of course R is the gas constant, T temperature, and P the pressure, and you have to do it in appropriate units. So this is usually given in millibar, and millibar is about 0.75 torr, 3/4 of a torr, and M here is molecular weight. So if you take in a simple example, you take the beam has to go through nitrogen, which is air, right? Air is 78% nitrogen, so we can approximate air as essentially nitrogen. So we take the molecular weight to be 28 atomic mass units, AMU, atomic mass unit, and then you take the temperature to be 300 K, right? Then you can plug these number, mass, molecular weight, and temperature into this equation, right? So here and here. And sure, you still need to know the pressure, but you can assume nitrogen, and so you can use these two quantity. You can plug this into here, and what you get end up is an interesting number. So you get P. So this three thing, right? So once you put in the number for molecular weight and put in the number for T, which is 300 K, and plus this number, right? Times P. So you get a number times P, right? And now if you want to, so at this number will give you the flux in terms of this unit. But if you don't want this unit, you want the flux in terms of monolayer, right? How many monolayers? So you have to know the quantity, how much atom, how much translate the number of atom per monolayer. And the number of atom per monolayer is usually is 3 times 10 to the 14 particle per centimeter. So that corresponds to 1 monolayer capacity. It's the surface density of a 1 monolayer, 3 times 10 to the 14. So you take this number, divided by whatever you got here, you change the unit. You essentially change the unit as number per surface density per cc squared into monolayer per centimeter squared per time. Okay. So what you end up is that if you do that, what you end up is that you have n equal to 10 to the 6, roughly 10 to the 6 times P. Okay. And the unit is the monolayer per second. So this is an interesting, simple thing to remember, right? For flux is roughly, for air, you're talking about air, room temperature, you would get about 10 to the 6 times P, and monolayer corresponds to a monolayer per second. And a guy by the name of Erwin Langmuir realized that way back in the 30s, and he was the guy who awarded Nobel Prize in chemistry for inventing this thing called surface chemistry. So he realized that, and everybody since then named this unit. This unit, defined unit called Langmuir unit, is named in honor of him. This unit is 1 times 10 to the minus 6 torr second. Okay, so 1 times 10 to the minus 6 torr second. So why this, right? Why this unit? Well, if you take 1 Langmuir, right? 1 Langmuir, 1 times 10 to the minus 6 torr second. So you take the pressure